Good morning everyone, I am Mr. Ish. Thank you for joining me. I promise you a very useful and interesting video over here. We have to prove that a coordinate x comma y in the second quadrant is always minus x comma y in terms of its representation. How do you go about understanding what the question is? You know, when you're looking at a Cartesian coordinate system, you have quadrant 1, quadrant 2, and then you have 3 and then 4. Any point over here, if you have the x and the y value, it's always minus x comma y. And why is that the case? How would you go about proving that? You cannot simply say that this is minus x here and in this direction it's positive y, hence any value here is intuitively minus x comma y. How would you do this proof here in a good, reliable manner, something which would have a certain benefit? And I will show you that in this video. Let's look right here with a certain point over here. With regards to this line, you project an angle out towards it, so that you're looking at something which looks like that. If you're thinking everything here with regards to a certain radius and a certain unit circle, x square plus y square is equal to r square. We've projected a certain angle in this direction. With regards to this line right here, now speaking in terms of angles, this measure over here is 180 minus theta. And you know that to be the case, 180 minus theta, because it serves as a reference angle for that angle you've drawn out and projected that ray at. 180 minus theta. When you're looking here at everything with regards to a unit circle, you end up seeing something like this. This is what we have in terms of our item over here, and then you have a unit circle. You have a certain point here, P, it'll have a certain value, x comma y. But we will know that value will be minus x comma y, and we have to prove that to be the case. We've determined this angle here to be 180 minus theta. What you can do is draw a right triangle over here, and this right triangle has a certain x dimension, it has a certain y dimension, and it has a certain radius r, because we're looking here at a unit circle which is the same radius all around. When you look at this value x, you're looking here at cosine with regards to this angle right here, 180 minus theta, which is always adjacent over hypotenuse x over r. When you're looking at everything with regards to the y, your y dimension, you have here sine of that angle, your reference angle, which is 180 minus theta, is equal to y over r. X over here is equal to r times cosine 180 minus theta. Y over here is equal to r times sine 180 minus theta. You've seen how everything has arisen here from the concept of a unit circle. But we have not fully answered our question yet, because we need to arrive at minus x comma y, and I'll show you. I will erase this so you can have the demonstration here done on this side. What will happen from each of these statements is that you will think about the trigonometric identity, which will look like a difference identity for cosine and the difference identity for sine, and you'll solve it. You'll have r times the difference identity for cosine is always here going to be cosine 180 cosine theta, and then plus. Remember, cosine x minus y is equal to cosine x cosine y plus sine x sine y. That's exactly what I'm doing here. Sine 180 and then sine theta. And then you'll do exactly the same here, but you will utilize the sine difference formula. Sine x minus y is equal to sine x cosine y minus sine y cosine x. You remember that. You'll have here sine 180 cosine theta, and then you will have the minus will retain. Here you'll have sine theta and then cosine 180, and then we'll solve these out. When you solve this out, sine of 180 is always 0, it zeros all of this out. Cosine of 180 is a minus 1. Minus 1 will hit with this cosine theta, and you'll get here a minus cosine theta. That's exactly what you'll have. When you look right over here, sine of 180 is a 0, it'll cancel out, is 0 out. Here you're just looking at this. Cosine of 180 is a minus 1. That minus 1 will hit with this minus, and you'll end up seeing r sine theta. So we know x is equal to r cosine theta with a minus here, and we know y is equal to this. But this minus can be projected here onto this side. As you see that to be the case, you have a plus over here. You know, in all instances over here, this point P on the unit circle is always represented as, you know, cosine of some value and sine of that some value, and I've shown you what that value is equivalent to. That value in all instances is always equal to some sort of x and some sort of y. You'll take this negative value and you'll project it onto the other side. You'll take this positive and project it onto the other side. When we project this minus sign onto this side and we project the positive over here, we know we end up here with a minus x in terms of r cosine theta, and we end up seeing r sine theta is equal to positive y. We end up seeing minus x comma y. If you look right over here, any point on the circle is always represented as cosine theta and sine theta. If you assume for your unit circle radius is equal to 1, this r value disappears and you end up seeing here cosine theta or minus cosine theta is equal to x, and then you can say cosine theta is equal to minus x, and in this particular case radius equal to 1, sine theta is equal to y, and hence you end up showing that any point in the second quadrant by means of this reference angle which has been generated with regards to what you have over here is always minus x comma y. Everything here stemming from the concept of the unit circle. Assuming you have a radius of 1, you very easily demonstrate this. Remember, this right here is one way of doing it. There are multiple other ways. I was just showing you a single way. But that's all I wanted to show you in this video. Thank you. Have a good day.